So it says the law of reflection states that when a ray of light hits a surface, the angle of reflection is equal to the angle of refraction. So what I take this to mean is you have a ray that hits a surface, and there's an angle, some angle. It bounces off, and the angle that it leaves at is the same. These are supposed to be the same.
Okay.
Now, if you have, again, full disclosure, like I'm not like the expert where it could be that one of these words isn't quite right, but that is the general idea here, is that angle comes in equals the angle it goes out.
Okay.
So we can go with that. Okay. Oh, and then question 2 here. Man, didn't even need to draw this. Question 2 has this nice picture, although I don't see there might be an angle down here. I can't really tell.
Yeah, I think I sent you another picture. It may have been.
Oh, there it is. I got it. Yeah. Okay.
Okay.
Let me grab that picture, and then we can talk about it. This will maybe help also. So this ray 1 is kind of well, this is your surface here, and a lot of times it's like air to water is the common example. Or you can think of it as a window, outside, inside. But the ray comes in, and it does bounce, but some of it also comes through into the other side, and you see that in certain things. I'm trying to think of a good example of that. I can't come up with one. But the theta 1s and the theta 2s, those are the same. Okay, and I know we're supposed to probably identify them. So let me try to help here. What does the drop down say next to ray 1?
Next to ray 1.
Like yeah, that says to choose, I think.
Oh, and you want to know the options?
Yeah, that would help here.
Angle of reflection, reflected ray, angle of refraction, incident ray, refracted ray, and angle of incidence.
Okay, so ray 1 is the incident ray. It's the incident means the start. Theta 1 is the incident angle, or angle of incidence, however that is termed.
Angle of incidence. Okay.
Yeah. Ray 2, and we got to go back to our terminology from question 1, is the reflection. So it's the reflection ray. So this one that bounces off, it's reflected.
Okay.
Theta 2 is the reflected angle, because obviously the angle is there. And that's where maybe I go back to question 1 here. Sorry to do that. Reflection and reflection. So the reflection, so this is reflection. The refraction is actually the one in here. So maybe I'll check that one. Sorry for jumping around. The word does matter. Law of reflection. Yeah, I guess I would go false here now that I'm looking at it again, because it's supposed to be the incidence and the reflection are equal, not the incidence and the refraction. So I would probably change that.
Okay.
Okay, back down here though, and then ray 3 is the refracted. So you can think of this as the refracted region. This is the incident, and this is the reflected.
Okay.
So we've got the refracted ray, if that's one, and then theta 3 is the angle of refraction.
Okay.
Is that okay? All clear?
Yeah.
Okay. Let me keep going here. All right. So the third question asks about, okay, so this, okay, here we go. Boy, there's another student I worked with where I had to sort of go through all the questions to like know which order to give them, and this would have been the right one to start with.
Oh, okay.
It's the angle of incidence is equal to the angle of reflection. That's what I've been trying to say this whole time. The angle comes in equals the angle goes out. That's the incidence, and that's the reflection. And that's really what we start with. And that's why number one is false, because it's talking about the refracted angle, which could be the same, but it's most of the time it's not.
Mm-hmm.
All right, so number, can I just put you on hold for just, oh no. Sorry about that. I've been waiting for a call back and I think I finally got it. Okay. So the next one is the, sorry, let me snip it in first. Oh. The reflection of a sound wave. So I you know, to me, the answer is like what we think it is, which is it's an echo. But because it's physics, I want to confirm that with a textbook or some sort of online resource. Yeah, so you know, that's just the traditional echo here.
Okay.
And it's odd that it's part of this problem set, but maybe they got mixed up. I don't know. I see another question here with a different image about A, B, C, and D. Let me grab this. So here's the next one I see. I don't know where that is.
Oh, that's the one that got split up between two emails.
Okay. Well, this one asks about A, B, or it says angle of incidence.
Mm-hmm.
I don't know what the next one, angle of incidence, that's A. So that's the angle made with the surface. You got your ray coming in, your angle made with the surface, okay? And then you have your angle of reflection, and that's D. That's the one that's still made with the surface, but it's made with the one going out. You can think of in and then out. And what I don't know is what I can't see in this email is if there's more that it asks for. Does it ask for other things here?
It's just those two.
Just those two. Okay, well, that will do it for those. And then, all right, so again, here's another question. Maybe it's not in this order but for you, but here's the way I see it. When a ray, sorry, let me snip this a little tighter. Okay, when a ray of light hits a surface, okay, so again, like here's your surface. I've done this like 3 times. Here's the ray coming in, okay, and yeah, we know it goes out, but this time, so the reflection goes this way, and the refraction goes this way.
Mm-hmm.
Okay. And it's measured from the normal. The normal is the surface. And so that's the line of the surface. Like sometimes you see this dotted line in books. It's supposed to be measured with respect to the surface that it's hitting.
Okay.
All right. I don't know where that leaves us at, but that's the first email as far as I can tell. What we could do is go to the second email and you could tell me if there's anything that was missed
Okay.
or something else. Oh, I see that. There's that question too. Okay. All right. So question one here, it says to match with the definition. And so I can sort of describe them. And kind of your test taking strategy here is you do the one that's easiest or clearest first. So like to me, either reflection or absorption is the easiest to talk about first. Reflecting, like we think about reflection, means like it goes opposite or bounces, and absorption means to, like, I don't know, include or covers. And transmission is like sending. So do any of the drop downs here, like do any of those words resonate? Do they match with you on what that?
One of them is the transfer of energy of a wave to the material it penetrates.
So that sounds like absorption to me. It could be transmission, but when it says transfer, that means it's taking it on.
And then there's one that says the movement of waves through material without absorption.
So that's movement. Movement's transmission. That's transfer. What's the last one for reflection?
The change in direction of a wave at a boundary between two different media.
Yeah, so change in direction. I mean, this is almost more like your standardized test reading stuff where you're looking for the synonym or same meaning.
Mm-hmm.
Most things you can deconstruct into that.
Okay.
A lot of this is really useful to see in demonstrations in class or labs, especially if you haven't seen some of these things before. But that, it's obviously not. It's kind of the fun part of physics and chemistry when you actually see this in action. Okay. You've probably done number 2. And when you drop the rock or throw one, you can see the ripples going out.
Mm-hmm.
The string's a little harder. What ends up happening is when maybe you've played an instrument, a string instrument, if you pluck it, you get these oscillations. They're hard to see. Sometimes it just looks like the thing is actually just like bouncing up and down, but there's actually these little waves on there.
Oh, okay.
Yeah. Tilting a water tank. I kind of don't get that. I don't think that one's included. I mean, you just pouring it out. If you were to pour it, say, into another water source where it was kind of feeding in like that, you might see some waves, but just tilting it to one side, maybe that's what they're saying. Like if you tilt it, maybe there's too much water in there, but if you can imagine having all the water kind of up along the one side here, and then it rushes out. Yeah, I don't know. I guess I would check it. If you get a second attempt, maybe don't check that one if you can see the answers.
Okay.
But that, I think that's the intent there. Okay. All right, the wave shown below is 1 second long. So they're telling you that this happens over 1 second.
Mhm.
Okay. The period is the first thing it's asking for, period. And it actually helps you out there. It tells you its units are in seconds. The period is peak to peak or valley to valley.
Mhm.
But we actually don't get the information we want here. You can see that it does one full cycle, call that's a cycle. And then it does another full cycle, that's 2. And then another full cycle, that's 3, 4, and then 5. So it actually does 5 cycles in 1 second. So the question is, how long does it take to do 1 cycle? Well, you're dividing that 5 by 5. So you divide that 1 by 5, and it's 0.2 seconds.
Mhm.
Okay, now, not to be confused, but it probably is, with wavelength.
Mhm.
So this is literally, and I hate when this happens, length of the wave when we're using that word in there, but it's the length of the wave. It's the start to the finish here. It's like how far horizontally is the wave. So you can see that this much is 1. This much right here is another one. Let me change colors here because I think it's too much to see. That's 1, that's 1, that's 1, and that's 1.
Mhm.
So there's 4 of those. So it's 1, 2, 3, 4 centimeters is the wavelength. The length of the wave, the horizontal component of the wave.
Okay.
And just as an aside here, all the communication that we do is done through waves, wireless and
Mhm.
transmission of signals. So this is, it's somewhat useful. Amplitude, but we're just making like we're trying to represent it in something that's like when you the string is probably the best example. When you pluck a string, you can actually see this, but you don't see the waves when you're making a phone call or transmitting data wirelessly. So
Mhm.
the amplitude is from the center line, and in your algebra 2 trig, I don't remember if we covered this in much detail, but from the center line, that center line can actually move up or down. But from the center line, wherever the center is, it's just how far up is it? How far vertical is the amplitude? So that blue there, you can see that's 1 and that's another 1. So it's 2 centimeters tall. So it's the vertical. In this case, it's 2 centimeters. So obviously, if they gave you a different problem with different things, you would get different results.
Okay.
All right, so new question here. I actually don't know what P dot D is referring to. So I'm going to look it up. A transformer, there are, so on your power lines, hopefully you've seen power lines around town.
Mhm.
There's usually like 3 wires. And then you don't see them very often, but near an intersection, you'll see some buildings, usually behind the gates, and some wires. These are your local sort of transformers. So they call them step down transformers, because they're
Mhm.
taking this stuff, which is at, I don't know, it's probably 240 volts. I really don't know, but they're stepping it down to what you get in your home. Because you can't run 240. I mean, some people have 240, but they step it down to the 120 volts that you're used to when you plug in your home. Because you can't
Mhm.
run this directly to your home. It would be really bad. So there's step down, and then there's also what are called step up transformers, depending on the situation. So they usually step it up from the power plant because it has to be at a higher voltage to run and a higher current to run longer distances. And none of that really matters until you don't have power. Um, if you have the ability, it might be neat for you to look at a power bill from your household, and just to see how
Mhm.
much consumption you use and the price. You'll find it's relatively cheap for what we get out of it, to be able to power our electronics and cool our homes and things like that.
Yeah.
So back to what you actually care about. And again, I don't even know what PD, potential difference. Okay. I guess that's, like, okay, so the PD refers to the potential difference, which I guess we'll write down, which is the voltage.
Okay.
And where is the, so none of these, excuse me. So there's generally, the most common way to generate power, and you've seen this in a generator, is you stick a wire through a coil, and then you rotate them, and they rotate in perpendicular direction. So I want to say it's the primary coil, which I think is what this is referring to here, this coil where you stick this conductor through a magnetic field. I'm
Mhm.
not seeing like a clear match to what's here, just partially because I'm not the biggest expert at this, but it is possible. I think it's still possible for us to figure this out. So I guess I would go with that. I'm not sure why there's a secondary coil. PD could also refer to partial discharge in a transformer. Yeah, I'm not seeing like a, let me try one more thing here. Okay, I'm gonna just move past that, and we can look at it later if there's an issue. All right. So we're getting to some numerical problems finally. Okay, if you want your 12.6 volt battery to power your new 200 volt aftermarket sound system, what is the required ratio of loops on the primary coil to the secondary coil? So primary to secondary, you can see that you have to multiply by 16. I'm using that based on these answers here. So all we got to do is figure out primary coil to secondary coil. You know, what is the, how do you figure out the ratio? And let me just look for an example to maybe give us the answer, because I don't know right off the top here. Primary coil to secondary coil. Sometimes when you're watching lectures, they give you, you know, an example problem that might be useful here. To be able to figure this out, but okay, so what I'm seeing is you need more turns for more voltage.
Okay.
Which means that your 200 volts going to have more turns than the previous one. So if we go primary to secondary, you know, for every one of those, you need 16 there, because that'll get you the greater voltage on the second one.
Okay.
All right, so next question. Okay, so now I'm back to like a question 1, which is on a refrigerator. I'm sorry, transformers can be used. Okay, so the question is can you both step up? I've kind of already answered this, to 150 volts, and can you step down to 10 volts? And the answer is yes. Okay, so yes, you can step up or step down to do this.
Okay.
So next question here will help us. If we knew the answer to the previous one with the more turns, more voltage, should help us to answer this. So notice, okay, so let's do primary and secondary here. The primary, okay, 50 volts and 20 turns.
Okay.
The secondary has 40 turns. Okay, so more turns, more voltage. So double the turns, double the voltage. And that's consistent with what we said in a previous problem. Number of turns, more turns, more voltage.
Okay.
All right, so it looks like we're moving to like we're back kind of to waves. There's some really interesting documentaries or science stuff on like the origins of waves and how they travel from their source to the beach. And, you know, the fact that they carry all this energy. I mean, they're very destructive in the case of like some of the incidents you've seen over in like Japan, in India many years ago. There's just, I mean, they're very powerful, but they're also very, very scenic, majestic, beautiful to look at. So what they're talking about here is that the wave itself is moving. Okay, but like it doesn't move, like it's not like the water is moving with it. Because I mean, if the water kept moving, it would build up on the shoreline. And if you've been to the ocean, which I think you have recently, I mean, or at some point in your life, you know, there's not a bunch of water there. It just recedes back.
Yeah.
So the energy is transferred without the matter in this case being the water. So I guess I would go with true. Is that okay?
Yeah.
All right. Okay, so question 2, and this is good that you show the drop down with it because it does help to be able to answer the questions. So the answer space tells us what we're looking for. So there's this idea of a transverse wave and a longitudinal wave.
Mhm.
And one of them will obviously carry, I think, sound, and one will carry, well, I don't want to speak quite yet, but they're it's like one. This is sort of a standard textbook thing here. So I'm trying to find a simple resource to explain this. They usually give examples and then give the definition.
Okay.
That's not very helpful. That's why they don't do that. Okay, so the water is the transverse. And the reason it's a transverse wave is that it's like we talked about, it moves, but the water itself is just moving up or down. Like it's not moving left or right.
Mhm.
Sound is what's called a longitudinal wave. Why is that again? So so the reason it's longitudinal, and you know that you can, I mean, you can actually understand this from what we're doing right now, but it's easier to explain if you're standing in a room. You're
Mhm.
here and someone else is there, you speak, right? But it's carried in the direction of the wave.
Mhm.
So notice, like in the case of water, the water's moving up and down, but the wave is moving right. Here it's moving in the direction of the wave.
Okay.
Not sure that's clear, but yeah. And I just confirm this. Sunlight is also transverse. Trying to think of why that is. So I'm bothered because usually there's one of each. So is water also considered longitudinal because it does move that direction as well? I think it is. So I think water is actually both because of that.
Okay.
This is again my best guess on that. Okay, that might be everything. You tell me though. Is there did we get to all the questions in the emails for this lesson time?
Yes, I think we did.
Okay, I know you've got another hour scheduled. Do you have more for us to look at?
Yeah, I have another assignment.
Another couple of things. Okay, well, let's break here and we'll pick up in about 20 minutes.
Okay.
All right. I'll see you shortly.
Okay, thank you.
Bye.